All right, have you ever tried to throw a frisbee on a windy day and it just goes completely haywire? Or maybe you've seen a drone struggling against a crosswind. Well, the answer to why that happens is all about combining these invisible forces. It's a concept called vector addition. And today we're not just going to do some dry math lesson, no way. We're going to learn to see the hidden code that guides pretty much everything that moves.
Okay, so let's just jump right in with a real-world puzzle. Imagine you're flying a drone. Your target is your friend's house, straight ahead, due north. Easy, right? But wait, there's a strong wind blowing from the side, from the west. So you push the joystick forward, aiming right at the target, but where does the drone actually go? Yeah, it's not as simple as pointing and shooting. To solve this, we're going to need a special kind of tool.
And that tool, the hero of our story today, is the vector. You've probably heard the word, but what is it really? A vector is just how we talk about any force that has both strength and a direction. You know, a push and a pull. So, before we can solve our drone problem, we've got to get a handle on what exactly a vector is.
So what is a vector? Honestly, the best way to think about it is like an instruction on a pirate's treasure map. It's not enough for the map to say, walk 100 paces. I mean, that's totally useless, right? A good map says, walk 100 paces due east. A vector gives us both of those critical pieces of info. The magnitude, which answers how much, that's our 100 paces, and the direction, which answers which way, that's our due east. You absolutely need both. And this brings up a really key difference between two types of measurements. If you're in your car and you say you're going 50 miles per hour, you're only telling half the story. You've only given the magnitude. That's what we call a scalar. You and I just call it speed. But the second you add a direction, I'm going 50 miles per hour north. Bam! Now you've got a vector. That's velocity. See the difference? Speed is just a number. Velocity tells the whole story.
All right, so we know what vectors are. Now for the fun part. How do we add them together? Let's start with the most intuitive way, the way our brains kind of naturally want to do it, by just drawing a picture. This method is perfect for getting a quick visual gut check on what's going to happen.
This is called the tip-to-tail method, and it's literally as simple as it sounds. So first, you draw your first vector as an arrow. Let's say that's your drone's intended flight path. Then, right where that first arrow ends, at its tip, you start drawing the second vector. That's the wind's push. So you have one arrow followed by another. The final answer, the result of both of them combined, is just the shortcut. You draw a brand new arrow from where you very first started to where you finally ended up. That new arrow is the combined effect of both forces.
Okay, drawing is great for a ballpark estimate, for sure. But what if you need to be precise? What if you're, I don't know, a NASA engineer plotting a course to another planet? A good guess isn't going to cut it. For that, we need to bring in the numbers. Let's look at the analytical method and see how it gives us a much more accurate picture.
So here's the big secret to adding vectors with numbers. You break them down. You can take any arrow, any vector pointing in some diagonal direction and describe it as a combination of two simpler parts. One part that goes purely left or right, we call that the x component, and one part that goes purely up or down, the y component. It's kind of like giving someone directions in a city. You don't say, go that way diagonally. You say, go 3 blocks east and then 4 blocks north. Same idea.
And here's why that's so powerful. Once you've broken all your vectors down into these simple sideways and up-down parts, the math becomes, well, incredibly easy. To find the final combined result, you literally just add up all the x parts and then you add up all the y parts. That's it. It turns what looks like a complicated geometry problem into just simple addition. It's so clean, it's precise, and it's super powerful.
Okay, we've got our toolkit, right? We have the picture method and the numbers method. It is officially time to go back to that windy day and finally figure out exactly where our drone is going to end up.
Let's start with the visual guess. First, we draw an arrow pointing straight north. That's our drone, trying its best to fly to the target. Now, using that tip-to-tail method, we tack on the wind vector, pushing it off to the east. So when we draw our final shortcut arrow from our starting point to our final endpoint, what do we see? Yep, it's obvious. The drone is blown way off course, ending up somewhere to the northeast of where we actually aimed.
Okay, visuals done. Now for the precise answer using numbers. The drone's aim is purely north, right? So its side-to-side, or x component, is 0, and its north-south, or y component, let's just say, for example, is plus 10 miles per hour. Now the wind. It's blowing purely east, so its x component is, say, plus 5 miles per hour, and its y component is 0. Now for the easy part. We just add the columns. 0 plus 5 is 5, 10 plus 0 is 10. So the drone's actual path has an x component of 5 and a y component of 10. We now know its exact path.
And that final path, the one we just calculated, it's got a special name. It's called the resultant vector. It's the one single vector that perfectly sums up the combined effect of all the other vectors acting on our drone, all the pushes and the pulls. That is the final answer we've been looking for.
So we did it. We solved our drone problem. But here's the thing. This method of adding forces isn't just for drones or model airplanes. It is a fundamental principle of how the universe works. Once you know what you're looking for, you'll start seeing vectors everywhere. They're like the hidden instructions running a huge part of our world.
So what are the big takeaways here? Well, you now have a toolkit for understanding how forces combine. You've got the picture method for when you need a quick, intuitive guess. And you've got the numbers method for when precision and accuracy are what really matter. And you know that the final answer, that combined result, is always called the resultant vector.
And this stuff really matters because vector addition is happening constantly, all around you. It's in the physics engine of your favorite video game, right? Calculating where your character is going to land when you combine a forward run with a jump. It's what a ship's navigator uses to chart a course that has to account for powerful ocean currents. It's even how your phone's GPS can take signals from multiple satellites way up in space and combine them to pinpoint your exact location on a map. It's pretty incredible. When you get right down to it, vectors are like a secret language the universe uses to write its own rules. They describe everything from the combined pull of gravity between planets to the mind-boggling forces that hold up a massive bridge, all the way down to the simple act of a ball being thrown on a windy day. They are the invisible instructions building our reality moment by moment. So the only question left is, where are you going to spot them next?